Hello, this is Tom from anti-proton.com, and I was recently asked about shielding. How do I shield my materials? How do you calculate for shielding? Those sorts of things. Everything you want to know if you have a collection of little nasties that, tick on a Geiger counter, like this guy. I'm going to make this short and sweet, since I have a tendency to make things too long. For me, short and sweet is probably 15 minutes, because I usually put out these hour-long videos. But regardless, I'll try to make this quick. I'm going to break the radiation down into alpha, beta, and gamma/X-ray, since those are both photons at the very end, X-rays and gammas, and their energies overlap, so there's always been a bit of discussion in the scientific community as to what the difference is between the two. But anyhow, and if you have any opinions on that issue, let me know. The only major opinion most people have is X-rays and gamma rays being man-made or natural, yet there are naturally made X-rays and naturally made gamma rays as well. First up on the list, alpha emitters. For that, I have polonium-210. Polonium-210 cannot travel very far through air. In fact, most alpha emitters cannot. Polonium-210's range in air, standard pressure, standard temperatures, is something like around 3.9 something centimeters. It isn't going to go very far. It won't even detect on the Geiger counter. The biggest danger of alpha emitters is if they get into you. As long as they're outside of you, they're virtually no danger at all. You could hold a uranium piece in your hand, and the alpha component of that will not even penetrate the dead skin layer on the outside of your hand. Now here's the problem. If alpha gets into you, not alpha particles themselves, but emitters of alpha particles, if they get into you, they're incredibly dangerous. I mean, they tear your cell walls to pieces. Horrifying, 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 horrifying. And so I keep my alpha emitter inside of a Ziploc, and then inside of its container. When I pull it out, I wear rubber glovies, like little latex gloves. Smart thing to do, cheap, easy to take care of. It's a very powerful source, gets a good tick on your Geiger counter. It decreases pretty rapidly over the space of 3 years, which allows you to do all kinds of mathematical stuff with it as well. So, the best thing to do with alpha emitters is put them inside of something like a bag. Be mindful of the fact that any bits of them that get off and get into your system are incredibly dangerous. And when you have things like uranium, for example, like here's a sample of uranium, do not believe that this only produces alpha. It also produces beta and gamma, either directly, indirectly, or through its daughter nuclides and isotopes, things it decays into. So just because it is an alpha emitter, like this alpha emitter actually does produce gammas occasionally. It's just so infrequent that it actually doesn't matter. But normally put some powerful alpha emitters, like americium-241, also produce a significant amount of gamma, and that should be taken into account. I lock mine up inside of this little container with a key on it. Anyone could get into it, I guess, but the point is it's not just going to pop right open, so keep it away from people. Next up on the list, beta. This is a strontium-90 sample. Let's see here. Okay, let me see if you can see this on the camera. It's in there. Strontium-90 decays into yttrium-90 by means of beta emission. Pretty powerful beta, too. However, oops, I hit the camera. However, I can't detect much of any of that from it. The reason is because aluminum is a very good blocker of beta emissions. The reason aluminum is because the number of protons in aluminum is so low that when the betas come out, they slow down, they attenuate, which is the change of intensity of any flux, meaning things like radiation, for example, which is what we're talking about, when they change, when they become less in intensity, less amount of it coming out at you at any given point, that change in intensity, if it happens too rapidly, can cause secondary emissions of gamma rays and X-rays. This is called the Bremsstrahlung effect, which of course is engine braking, yes, engine braking. Radiation braking in German. Why we chose that word, who knows, but it's a German borrow word. So if you use things like this, like lead, that's fine, but the problem is you're going to produce gamma radiation as a result of it, secondary gamma. So aluminum is an incredibly good substance, anything with a low proton count. And if you get a periodic table of elements, those very first elements, hydrogen, helium, so on, those are the right ones to use. I'll show you in a minute how to calculate this, but basically put a couple millimeters of aluminum like this little lead pipe, I'm sorry, not lead pipe, this aluminum pipe, do an incredibly good job of blocking the strontium-90. It just doesn't get through. However, to give you an idea, oops, let me make sure the right part of that's exposed. My cat's running around, by the way. He keeps bumping into the stuff. Obviously it's there. So aluminum works great for beta emitters. And if you have an alpha emitter, you could take something out as aluminum and you could put the alpha emitter inside of a baggie and put it inside, then put the beta emitter inside too. That would be fine. By the way, keep in mind to always be mindful of whether your samples leak out any gas or dust and keep them contained. These sealed samples like I have from Spectrum Techniques, they're supposed to be fully sealed. I mean, you could, in theory, you could wipe them off with something and test the wipe and get nothing off of it. I still always pretend in my mind as though they were contaminated. That's just a safe practice. They probably aren't. The outside surface area is supposed to be completely cleaned. But, you know, why be sorry? Now you get into gamma emitters. Whenever you have something significantly powerful, you should mark it as what it is. This is not a very good sticker, but it's what I have. I have, what is this? Let me pull the top off. I think this is about a 1/2 inch of lead. And inside is, let me flip it over so you can see it. There, let me see if you can see it now. Inside is 1 microcurie of cesium-137. Is it in there? Let's see. There it is. But the betas it puts out aren't particularly strong. Neither are the, well, the numbers of them in the gammas don't get picked up very easily by the Geiger counter, so you don't see very much. Now, storing it in this container right here blocks most of the radiation coming out of it. I recommend things like this lead pick. I got it from Spectrum Techniques for about 45 bucks. It's pretty heavy. Lead is an incredibly good substance for stopping things. If you go on eBay, you can buy these little lead ingots like this guy right here. You can stack them, always inverted like this so that you don't get any cracks in between. And by the way, keep that in mind. If you make a big stack of these things and put something behind it, little cracks, let me see if you can see this, the cracks in between, if they're wide open enough, radiation will move right through those cracks. So just keep that in mind when you're stacking these. I recommend buying lead bricks like this and you're spraying them with polyurethane spray. You just put them on a paper towel, and you spray them, wait about an hour, flip them over, spray them again, and you do this 4 or 5 times until they're heavily coated. This way the lead is inside of the coating, so it doesn't get on my hands. I still wash my hands afterwards, which is always good practice. Always practice good hygiene when playing with these sorts of things. But look at the effect. Let me show you. Obviously, picks up the uranium just fine. Put it inside of the lead. Alright, if you take the lead blocks and you take the piece of uranium like this, and as you can see, uranium is definitely hot. You put it behind, and then you stack the blocks over top. There, I had a crack. You're still picking up stuff, but not like you did. See? That lead really makes a difference. And a second block basically stops it. So I suggest using lead if you can, but you're going to have to use at least 1.5 inches of it or so. Which will bring me into the last part of the video. Now let me also point out things like this glassware right here, this depression glassware. Let me move this away. And in fact, let me stack these up so we're not getting much from them. See, the wall immediately works for me. So I get over here, and I'll get basically nothing. When you have things like this glassware, you don't get much from it. 100 counts a minute. Maybe 100 counts a minute. Even in back a little bit, it goes away. Things like this are so low that they can almost be safely kept in the room. Generally speaking, though, as a rule, you never keep any of this stuff around people, pets, children. Never let them near. They don't need to be near it. It doesn't matter how safe it is. You don't need to let them near it. And remember something about uranium glassware. Treat it like lead glassware. Alright, don't put stuff in it like tomato sauce. First off, you shouldn't be eating in it at all. I mean, good God. But if you are so crazy as to eat out of it, don't put anything acidic in it because it'll leach the uranium out. Honestly, you shouldn't be using it at all. But if you do, there you go. Now, I suggest taking things like this. This is a piece of lead. This is about, I don't know, 4 or 5 millimeters of lead. And it's wrapped in aluminum. It's wrapped in many sheets of aluminum. The point being is the aluminum helps to slow down the beta and alpha particles. Well, it stops the alphas, but slow down the betas before they get to the lead, and the lead stops whatever comes out. These little sheets are incredibly useful when trying to block stuff. And they stop radiation from things like this nearly completely. I mean, it'll still get through a little. That should take at least a little. There we go. But not much. It might just be background. Alright, now for a few calculations. Just to let you guys know, I keep all my stuff in my lab, which is away from where I live. I don't live in my lab. I don't sleep in my lab. It's nowhere near me. I practice several particularly important rules. First off, hygiene. Always wash your hands after you touch this stuff. Anything that could potentially have any loose matter to it usually takes rubber gloves. And remember, time, distance, shielding. Time means that no matter how much exposure you get, the longer you're around it, the worse it is. That's kind of sort of obvious. Distance. The further you are away from something, and you'll understand this in a minute when I show it, the less you're going to be exposed to, no matter what the intensity, because a certain amount of energy as it expands has to fill a greater and greater and greater volume of area as it expands. So this much energy as it expands becomes less and less for any individual point. I'll explain that a little bit more in just a minute. And then finally, shielding. Proper shielding, like that lead right there, ridiculously reduces the amount of energy that comes out of something. Remember, there's not a humongous difference between radiation that comes from these things and background radiation. The big difference is intensity, the amount that's hitting you. So if you're only getting 14 counts per minute in your room with your Geiger counter, and you move these far over into a corner and put them in lead shielding, and then your counts per minute go up by maybe 1, you're not really being exposed to a particularly large amount of radiation. So keep that in mind, but always remember the last thing here, and that this stuff is can be very dangerous. Don't play with it. If you don't know what you're doing, don't mess with it. So, alright, now let's look at a little bit more. Radioactive materials produce rays of energy, which fly generally uniformly away from the actual substance in every particular direction. These lines of energy are called flux. The energy that's being radioactively emitted is called flux, and as they pass through things. And this energy has a certain sort of a quantitative amount, if you like. You can call it intensity. It's the measure of how much is coming out at any particular moment. And when you're trying to shield, it's very important to be able to calculate these intensities and the change of intensity. And we're not going to go into anything complicated like calculus here, but we're going to stick with some basic stuff. Let's start out with a point source. Here is your source. It is emitting radiation. However you want to look at that. You can say you detect 400 counts a minute from it. It has a certain activity of X number of becquerels. Who knows? Doesn't really matter for our purposes. If you want to get down to it, the correct way to measure it would be to determine how many becquerels of activity it has, and then of course what you detect on the other side. But regardless, it has lines of radiation that leave it. See? And these lines go every single direction too. Every single direction equally. Radioactivity is very random. Now to give you an idea, if I take an object and draw the object right here, this block of wood, this sensor, whatever it is picking up 5 of these little radioactive lines of energy. If I move it to here, approximately the same size. I might have even made it a little bit bigger. It's only picking up 3. Move it just a little bit further back. It's only picking up 1, so it's rapidly diminishing. What you're kind of hopefully sort of getting from this is that the amount of energy that's coming out is being evenly distributed over an ever increasingly large sphere. See? Sphere, sphere, sphere. So, how do we calculate for this? This is not shielding, this is distance, which is very, very important. How do we calculate for this? You've probably heard the expression 4 pi geometry thrown around a bunch with nuclear sorts of things. So let's kind of get an idea what this means. 4 pi geometry is the surface area of a circle. So here's your circle. The surface area of this circle is equal to 4 times the symbol pi, 3.14, yada yada yada, multiplied by the radius, which is, if you take a central point and draw a line out to the side here, that's the radius. All the way across would be the circumference, or not circumference, the diameter. The circumference is all the way around like this. Okay, so radius squared, because we're working in multi-dimensions here, specifically 2. Now, this is the area of the sphere. Okay, and all you have to do is divide the energy into it, and you'll get the answer. So, let's see if we can figure this out, okay? Let us say that our dot, I'll give you just a simple practical example. Our dot is a sample of uranium you bought off the internet, okay? It produces, you detect from it, let's just say you detect 400 counts per minute when you put your Geiger counter up close to it. I'm giving you a practical example. I'm not going to get down into the exact specific activity of it because you probably don't have the equipment to detect that anyway. Most of us don't. 400 counts per minute is what you're detecting. And you want to know at 4 meters distance what you should be detecting. This is above background. Okay? Let's use the formula. 400 counts per minute. This isn't really an energy unit, but we can use it. And I should say that this is more of, we'll call it X and call it quantity. That might be a better way to describe it. 400 counts per minute multiplied by 4 times pi times radius squared. Now, let's do the math. Alright? We know the radius. We know that the radius is equal to 4 meters. So let's write that down. 4 meters squared. Okay, now let's do the math here. 4 squared, let's see, 4 times 4 is 16, 32, I think it's 64 off the top of my head. Let me double check that. Alright, brain lock. 4 squared is 16. I'm thinking 64 for some reason. So we know that this equals 400 CPM over 4 pi 16 meters. 16 times 4 is 64. So we can erase this and we can say pi 64 meters. Alright. Now we just do the math. 400 divided by pi times 64, and then we hit enter, and we equal 1.989, and I'm going to leave it there. The number actually goes on for quite some distance. Alright, so at a distance of 4 meters, we expect that our 400 counts per minute has dropped down to 1.98, call it if you like 2 counts per minute. Simple as that. And just if we wanted to, let's do the quick math. What would happen? That was at 4 meters. At 3 meters, it would have been 400 divided by, I can just do this really quickly, 400 divided by, in fact, I'll pause the video for a second. Here I did the math for you really quickly. For 4 meters from the object, and I rounded these numbers up. I rounded them up, less than a couple tenths of a decimal place, etc. For 4 meters, you get about 2 counts per minute from your 400 count item. From 3, you get 3.5. From 2, you get 8. And from 1, you get 32. So you kind of get the idea that distance rapidly diminishes the ability of radiation to harm you because it decreases the overall intensity per any square piece of area. So after you do this math, of course, you also want to then multiply it by the surface area of whatever's touching it, like your whole body, for example, too. Because whereas this dot right here may be only hitting 1 square meter with a small amount, how many square meters is my whole body? So you have to take that into account as well. Moving right along to the next part. Alrighty, when blocking radiation with objects, concrete, lead, balsa wood, doesn't matter what you use, it's important to be able to determine exactly how much you actually need. And when you're on the computer and you're looking at something expensive and you're trying to decide whether you need to buy it or you need to buy double, I mean, how many millimeters of lead shielding do you want to buy? It's important to have the math to figure that out. And of course, while my video does not constitute any official advice, let me just tell you how I do it. So you can watch and see how I do it, and then you can decide if that interests you in any way, shape, or form. I use a pretty simple equation. I wrote this down because I hate doing the math on the calculator the whole time, and it's much quicker. My video is drone on too long otherwise. Here's the equation I like to use. The intensity after I go through a solid object is equal to my starting intensity multiplied by Euler's number, which is E, sometimes mispronounced Euler's number. And I usually like to raise that to the power of the natural logarithm of 2. That's a negative in front of that, by the way. Negative natural logarithm of 2 over the halving value, h sub v is what I put in, of the object. I'll tell you what that is in a second. And we'll call it x, the amount of the object. Now, halving value is the amount of something required to, on average, decrease the radiation going through it, the flux, by half. If you imagine somebody shooting a gun through a forest, the thicker the forest is, the more bullets it's going to stop, because the bullets will hit trees. But there will always be a chance that a bullet will make it all the way through. And so that's why you don't say this is the value required to stop everything, because you don't actually know. There will always be a little bit that makes it through. But typically, over time, given math and probabilities, we know that a certain amount of something will typically reduce the intensity by half. Now, it is incorrect to go on the internet and look up the halving value of, let's say, lead and say, well, this is the halving value for lead. It's always this. This number of millimeters always reduces the amount of radiation hitting lead by half, or whatnot. That doesn't actually come out correctly. And the reason is that the energy of the particle makes a difference too. I'm going to tell you that the halving value for lead, the halving value for particles, for gamma rays, if you like, gamma rays, equal to or less than 1 million electron volts, meaning if they're above that, the halving value changes, it gets higher. But for 1 million electron volts or less, the halving value will be 8.61 millimeters. Put that over here. That's the halving value, 8.61 millimeters. Let's get rid of this. I'll show you how to solve for that. So you go to like Wolfram Mathematica and you type in the stopping power of lead for a 1 million electron volt gamma. Bing! And someplace like Wolfram Mathematica, they're really great. They'll spit out a number for you. You can do the math too, it's complicated, or you can do experimental physics and figure out, but just go to Wolfram, it's much quicker. And they'll say, okay, well this 8.61 millimeters is the halving value of lead for 1 million electron volts or less. Okay, so now you know this. Okay, how many do you need to do something? Let's say you bought that rock. That rock that's the 400 count per minute rock. And you know that probably, you looked it up on the computer, you know it doesn't put out more than 1 million electron volts of energy in a gamma. You know, you look up the uranium, the lead, whatever's inside the rock, and you figured this out. So you figured this is probably good enough. But you can't deal with more than 50 counts per minute, right? 50, I think that's what I did the math for, right? Yeah, 50 counts per minute. That's the max you'll deal with coming out of that lead. And you want to make sure that the amount of lead you buy is enough. So let's figure it out. Here's how you do it. Okay. Got this all written down here as a cheat sheet. Why? Because I'm lazy. I was at a dentist office this morning and I was writing this down as I was at the dentist office and double checking my work to make sure I didn't do anything stupid or wrong. I have a tendency to make errors when I do algebra. It's terrible. Okay, so 50 counts per minute is what we want. Divide that right off the bat by 400, which is what we have from the rock. And we know right off the bat we're trying to drop the number of counts per minute by 1/8. Right? 1/8? Down to 1/8 of what it was. 1/8. That's simple enough, right? What you want divided by what you have gives you that. Okay, simple enough. So here is the equation. 1/8 equals E, Euler's number, raised to the negative natural logarithm of 2, it's on your calculator, 8.61 millimeters. Now remember, that's the halving value. Always put the halving value there. And on this side right here, we're going to put in x. X is what we're trying to solve for. How much of this stuff we need. Okay, how many millimeters do we need? Alright? And this will be millimeters as well. Okay. Now the first thing we do is get rid of this nasty e. So we'll take the natural logarithm of both sides. Okay? Natural logarithm of 1/8 equals natural logarithm of e to everything that's up here. ln to 8.61 millimeter x mm. I haven't done anything to the problem so far except that I put these two little natural logarithm pieces right here. And what do? The natural logarithm of e to the anything is just the anything, right? So e to the n, the natural logarithm, is just n. So that's what happens. And the natural logarithm of 1/8 is negative 2.07944. You can just get in your calculator and hit the ln button, and then the number 2, or sorry, the number 1 divided by 8, and then enter, and it will spit out this number. You don't actually have to know how to do it. If you want to get into logarithms, you can actually figure out how to do it. It's not complicated to do it either way. Okay. And then now we have this. Alright, now we solve this baby right here. We take, let's see, what do I do here? I type in the calculator, I type in ln 2 divided by 8.61. Right, that's what I type in. And I come out with 2.07944, same as we have here, equals negative 0.0805, same number of digits here, multiply by x millimeters. Okay, and this millimeter here and this millimeter here, well, we can square these, right? No, we're not squaring these. Oops, let's get rid of those millimeters. No, I need them. In fact, let's get rid of all these little millimeters here. Just don't even worry about them for now. I'm not carrying my variables very well today. I've had a long day. I had very little sleep, so ignore me. So anyway, the next thing we do is we divide this side by that number. In fact, we divide both sides by that number. Algebra means doing it the same way on both sides. These cancel each other out. They're exactly the same. They factor each other out. And here's x. Leaves x remaining this divided by this. And the result of that is, where is it? Here we go. The resulting number is 25.83155. So we'll write the millimeter on the end. We cheated. Okay, so you kind of see what I did right here. I took this and I solved for x. And I ended up with 25. And now I know that if I type 25 into the calculator, because I did it, if I type in 25 into the calculator, it comes out correctly. In fact, I'll do it right now. If I take 50 counts, well, it's 1/8. If I take 1 over 8, 1 divided by 8 is 0.125. So I take 0.125 equals, now I take, oh, what the hell is it? E raised to the power of negative ln to, I don't know if you can see that, probably not, ln to divided by 8.61 multiplied by, what is that number, 25.83155. Now I shortened some of these numbers here. I didn't go as many decimal places as there originally were, so the answer may not come out right, but it'll come out pretty close. 0.124, which is 1/8. And 1/8 of 400, we can multiply that by 400, and we come out with 49.99, which is just a few decimal points, which is what we rounded, off of 50, which we just happen to know is the result. How do we know how do we know that's the result? Because that's what we wanted. We wanted to cut 400 down to 50, and we did so with 25.83 millimeters of lead. So there you go. That is how you solve that. Distance, time, and shielding are how you protect yourself. You can look up these values, these halving values, for anything you want. Some of you might recognize this formula. I've shown it before. It's actually the same thing as the decay equation for calculating exponential decay. And it's the same sort of math you're doing. You're actually just rewriting the same equation. It's one of my favorite equations. I use it all the time. When you write it for decays, it looks like that. A little different. E to the whatchamajigger T. Is that landed off the top of my head. Alrighty, well, this has been Tom from anti-proton.com, and hopefully my math hasn't frightened you. I'm really terrible when I draw it out. I always do a poor job, and I like to take my time and use my notebook. When all fails, you should always use your notebook, and you can do all kinds of crazy math gibberish in your notebook. Very, very, very important when you're doing the more calculated stuff like this, such as trying to figure out scintillators and all these sorts of things. The math gets really crazy. This is Tom from anti-proton.com. Bye-bye.